And 3, 2, 1.
All right. Oh, hey. Sorry, my dog just decided to bark. And yeah, that's good. Luckily, it doesn't bark for long. So my name is Kip Daugirdas. Hi. I am doing a presentation on flying really, really high. So I was gonna start with a video, and then we can go into a presentation. The presentation's not going to be crazy long, but then there's going to be hopefully 20 minutes for like Q&A. So yeah. So anyways, let's instead of listening to my dog, we'll listen to the video, give that a watch, and kind of go from there. So give me the opportunity to get this in here. And
Launch detected. Booster burnout. 20,000 feet. 30,000 feet. 35,000. Sustainer ignition. 40,000. 50,000 feet. Sustainer burnout. 80,000. 100,000 feet. 120,000. 140,000. 160,000. 180,000. 200,000 feet. 220,000. 240,000. 260,000. 280,000. 290,000. The Apogee deployment charge has fired. Max altitude 293,485 feet. Max velocity Mach 4.18. Apogee was northwest at a distance of 10.6 miles. 285,000 feet, descending at 780 feet per second. Now drifting.
All right, so there you go. Years of work for a 2.5-minute ascent, but it was a pretty amazing day. I have to say it was probably one of the best days of my life, if not like the best day of my life. I was totally floored that everything worked, and it was really, really cool. So let's see. I'll share my entire screen, and let's get into the presentation here. All right, so you guys hopefully can see my screen, yeah? What about now? Yeah? No?
No?
Hang on. Give me a second here. All right. Let's do the window. That should work. What about now?
Yep, gotcha.
All right, cool. Sweet. Okay. So this presentation is going to be a little bit about that flight, but also kind of go back into the history of like previous flights and attempts that I've had. This isn't my first, I guess, high altitude rocket. I guess high altitude to me is like, I don't know, anything over 100,000 feet is pretty up there. And I've had a good handful of attempts to get a chance to fly up there. A lot have not worked. Some have. When they do work, it's been pretty spectacular. And so we'll go through that, and then we'll answer questions. All right. So who am I? I'm sure a lot of you don't know who I am. So my name is Kip Daugirdas. I'm 37 years old. I've been in rockets for, since like 7th grade. Started building the Estes stuff, and got into high power early in high school. It was before they had Tripoli or NAR mentorship, so I'd always fly under my dad's name. My dad was not in the hobby at all. He facilitated it, which was great of him. Yeah, I basically built the rockets, and then he pretended they were his. And then he got certified, and then when I got 18, I went and did level 1, 2, and 3 pretty quickly. So kind of the top row is a few of the rockets that I built. I got to like pretty large 2-stagers. I'm originally from Chicago, where you see the big star. So I couldn't fly very, very high. So the type of rockets that I was flying were these kind of large would go 10, maybe 15,000 feet at most. But I also had a big interest in aerial photography and strapping video cameras to rockets and just regular photo cameras. So back then they didn't have GoPros, so we would stick like an entire camcorder in a rocket, and you needed a pretty big rocket for this. Pretty much like 6-inch diameter was the smallest size airframe you could fit one of those large cameras into. I went to school at University of Michigan for aerospace engineering, and that's when I started to kind of change my interest into wanting to fly, higher, faster. I kind of felt like I had done a lot of the larger, traditional high power rockets. And my senior year, I went to BlackRock for the first time, and tried a 3-stager, which you'll see in a later slide did not work. Anyways, after University of Michigan, I graduated in 2008. I went and worked for GE aircraft engines. I worked on afterburners, which was really cool. But I lived in a small apartment in Boston. I didn't have, obviously, a space to work on rockets. So I continued to pay my dues towards Tripoli, but didn't build anything. And then in 2012, I got the opportunity to move to Utah, mainly to ski, because that's something I really enjoy doing. Yeah, moved out there and switched my like 1-bedroom apartment for a house. And so all of a sudden, I had, a space again to build. And that's kind of when I kind of decided I wanted to get back into it. So at the same time, around 2012, there were groups in Tripoli vying for the Carmack Prize. The Carmack Prize is like a $10,000 prize to fly a rocket successfully to 100,000 feet, get GPS proof that you flew to 100,000 feet, recover the rocket safely, and write a report about it. This ultimately went to a group out of California, Aeropac, which you might be familiar with. They flew to 104,000 feet. And the amazing thing was not flying to 104,000 feet. The amazing thing is what they did, how they got to 104,000 feet. And they did it with pretty much the smallest rocket, at least that, people in high power had achieved that altitude with. So it was an N booster to an M sustainer. So it was only about 21,000 Newton seconds. And to reach that altitude with that kind of rocket, it really opened up my eyes because it was like, well, I have those 2 casings. If you remember those, rockets that I showed you beforehand, they flew on those types of motors. And so I think it opened up the possibility of being able to reach those high altitudes with, motors that were, I guess, just kind of easily attainable for regular rocketeers like myself and individuals. So, I thought the Carmack Prize is really an amazing thing. I thought it was really cool that Aeropac won it. And I still think like this quote that's on this slide right now still rings true. Like going 100,000 feet is not easy. I think it's an often overlooked goal even today by a lot of teams and groups that are vying for these high altitude flights. I really do think like it's far from routine. You go to BlackRock on any given year, and still to this day, maybe only 1 or 2 rockets make it over 100,000 feet, and it's oftentimes the same people who are doing those flights. So yeah. All right. So just to prove to you that it's hard, this is kind of just a list of a timeline of flights that I've done. So starting in 2007 with my flight with the University of Michigan, I think we got the most loop-de-loops ever at BlackRock. It was very many. I think the rocket only made it, to 1,500 feet. And even when I returned back in 2013, that was a failure. And the failure was I put in a flight computer upside down. These projects are just so much work that I just wasn't even prepared for the amount of work that they were. And just some dumb mistake in the early morning hours before a flight. And basically cost me that launch. you know, and slowly, you know, I would get a success here and there, but for the most part, you know, I was failing a lot more than I was succeeding. And by the time 2019 came around, I basically lost the entire project. And I knew that like something had to change. So in 2019, you know, I pretty much sat down, stopped working on a future project that I would do, say in like 2020, because I was flying these at a cadence of about one a year, maybe two a year, and I wanted to basically figure out why my flights were failing. So why do my rockets fail? So like in 2007, most loop-de-loops ever. That was purely just a lack of experience. Yeah, I had built some large rockets, but unfortunately, the experience that you get from building, you know, large level 3 rockets doesn't really transfer to building these high performance rockets. The other reason is, you know, go fever. Like you set a date, you have a launch ahead of you, and it's kind of like, you know, all or nothing to try to get it done. And oftentimes that never works out in your favor. I don't think it ever has. I don't think I've ever rushed for a launch and had it kind of turn out well for me. The other thing is not a lot of testing, and I don't mean so much ground testing, because you can even have tests for these high altitude rockets that work fine on the ground, but don't work at altitude. One of those, an example of that could be like your deployment charge. Your deployment charge might work great, you know, at home in an atmosphere, you know, on the ground, but once you get up into like a more space-like environment, they can tend to fail. And then another one was I failures. So, you know, I had a motor failure in 2019. It was a commercial motor, but it was nonetheless, it failed. And I've also had a string of no lights where the second stage never lights. So there were a lot of issues, I think, even though I gained like some, you know, some success, and I think there were still some major problems. So like I kind of alluded to, the things that can be done differently, you know, more ground testing, but particularly more flight testing. Um, and by flight testing, I never had a rocket where I could do any kind of flight testing, because I was always trying to get these, you know, once a year annual big projects off the ground. And that didn't leave me a lot of time to try new ideas and test my assumptions. With these projects, there's also always the allure to um, try to improve things even after you've tested them. So what I mean by that is like, you know, you say you test a rocket motor, an experimental one of your own, and you maybe see some areas of improvement that you could, you know, implement on the next motor, and you decide to do that on a flight motor instead of retesting it on the ground, you know, ensuring that it works, that performs like it should, and you then have an issue or problem with the motor and the motor blows up. So I think it's really important that, like, if you have not tested it, if you've not flown it, you know, sticking to what works is super important. Slowing down, what I mean by that is pretty much just taking your time. Um, don't I think like deadlines are important, like having launches as deadlines is important, but um, I think it's very important to really just go at the pace of the project and not really, if you don't hit a launch, you don't hit a launch, and you shouldn't try to cut corners to try to hit that launch. And then the other thing was I wanted to build my own motors. Commercial motors are great. they're awesome. But the options, once you start getting into like, you know, N's and O's, the options start to dwindle. And also rockets, like I talked about earlier, they're built differently. The motors are really like an integral part of the airframe itself. You're not really sliding them into motor tubes anymore. So you know, I wanted to start designing my own motors, not because I wanted to tailor their performance, but also because I wanted to be able to integrate them how I wanted and how worked best for these types of projects. So, all right. So in fall 2019, I decided I wanted to get into making my own rocket motors. And I pretty much told myself that I wasn't going to fly again unless they were with my own rocket motors. So I think that was like a pretty good impetus to kind of like get moving and start designing and developing a propellant. And so, you know, I spent essentially 6 months, about till like the middle of 2020, just developing the propellant that I wanted for a 2-stage project. And so, you know, progress in 2020 was really slow. I went from flying, you know, these big projects with N's and M's and you know, to basically these 2-grain 54 millimeter motors. And I struggled. I had some issues, some failures, some bad propellant. And 2020 was really like a foundational year where I kind of like definitely set the, you know, I don't know a great way to put it, but like yeah, it was a pretty foundational year. I did not fly a rocket. All I did was motor testing and propellant development. 2021 though, the pace picked up. You know, I selected a propellant and then it was starting to learn how to make the motors, and I slowly went up to larger and larger motors from 54s to 75s. So from like L's and K's to M motors, to actually, let me turn on my pointer here, and you know, actually doing like 1/3 scale tests of like the mesos booster motor, and doing a, you know, full scale 2nd stage motor test, and then starting to fly the motors that I tested. So that really helped me with like my confidence, and it gave me a lot of practice, you know, making, building and flying these motors. So all in all, it was a pretty massive effort. Like it says in the statistics, 34 motors, 7 of which flew. I mixed over 150 pounds of propellant, and that was for motors that I fired. Developing the propellant, I probably mixed an additional 30. So that's upwards of like a Q motor worth of propellant that was mixed to develop just an O and an M motor. So I think when you have like Gary Rosenfeld develop an O, or you know, CTI develop an O motor, you should give them a hug, because I think they've put in a lot of effort into getting to that point. So it's a lot of work. So I talked about test flights. So I developed this, you know, this rocket. It was just like a 4-inch diameter with a 3-inch motor mount. I named it Test Tube. Seemed like a good name for it. And it was really there to test my assumptions in terms of recovery, avionics, and payload. So Test Tube was built exactly like the booster and the 2nd stage of Mesos is built. So, you know, it gave me the opportunity to test like my charges, my drogue location, my dual deployment system for the rocket, the avionics, to help me test the launch pad even that I was going to be using to launch the Mesos rocket. It'll select what I was going to do for the GoPros for taking the onboard video for the flight. That wound up not being incredibly straightforward. And I uncovered some things that had worked for me in the past, even at 150,000 feet. I wound up having 2 apogee primary charge failures on test tube, which was like pretty scary because these charges are designed to work, in a vacuum. So the fact that it failed at, 6,500 feet and then again at 19,000 feet showed that clearly I was doing something wrong. And I'm glad that I uncovered it because it could have easily happened on one of my high altitude flights. So that's kind of the flight testing that went into the project. And so I wanted to talk a little bit about just my approach to flying these projects. So obviously everybody knows that, we live in an atmosphere and it gets thinner the higher you go. So it's incredibly important for these small 2-stage rockets that you deliver the energy from those rocket motors in the most efficient manner. Because if you don't, you're going to lose a lot of that altitude and energy to drag. And so it's very important. Like, this is just the drag equation. This is for subsonic, but it's still like the principles still apply, if you're going to be flying supersonic. Drag goes up, exponentially. So if you're going to be flying fast, you definitely want to be doing it, while you're pretty high up. And that helps you in a lot of ways. You get less drag, so you get more performance, which is great. But at the same time, when you start flying, close to above Mach 2 and getting closer to Mach 3, things start to get warm very, very, very quickly. And so, components can start to fail, particularly if your rocket's made out of, composite. A lot of composites are not designed to handle, temperatures above 200 or 300 degrees. So that's another consideration. So kind of going into this whole idea of, drag and wanting to fly fast, but wanting to do it at a high altitude. Here's kind of a very simple table. I picked 4 commercial rocket motors. So in the first column, we got an N2500 to an M685. And so that's basically a short burn booster to long burn upper stage. And you see that you get, pretty high velocity at a pretty high altitude. And you get a really good apogee. Next up, I took a long burn booster motor, an N1000. So an N1000 burns like 10 seconds versus an N2500 about 5. And you notice that, putting a long burn booster motor really doesn't buy you much. It buys you about 5,000 feet of altitude. And it really doesn't buy you much in terms of altitude where you see your maximum velocity. And generally a long burn booster motor, it has a pretty good spike at startup, but that thrust drops off very quickly. And so, the chances of the rocket, weathercocking or gravity arcing increase with the long burn booster motor. The booster, you really want to pretty much deliver that power and just get rid of it as quickly as you can and fly on the upper stage. And so on the third row down, you got an N2500 to an M1850, 2 relatively short burn motors. And notice the huge difference in max velocity and where it occurs, at what altitude. And you get a massive hit in terms of the final altitude of your rocket. So kind of the formula for these types of high performance flight is you really want to stick with, a short burn motor for your booster and a long burn motor for the sustainer. And there you go. You got the second stage boosting away. Okay, so taking that, I wanted to design some rocket motors. So, for me personally, I really want to see like a 15-to-1 thrust to weight ratio on the booster motor. That is enough kick off the pad to provide a straight boost, but not so much that you start having like excessive like stresses on the airframes. Obviously, there's drawbacks to that, right? So if you have too high thrust of a booster, obviously you need to make your airframe a lot stronger. It becomes heavier, and that booster's cranking out that thrust again in denser atmosphere. So burning out at 6,000 feet versus 10,000 feet can be a performance hit as well on your booster motor. So this is kind of like the Goldilocks motor that I designed for mesos. Here's the thrust curve. So you got thrust and pressure. And I was really surprised at the motor when I fired it off. It performed incredibly well with a good ISP, good and good peak thrust, and just a very flat, nice curve to provide that initial boost. For the sustainer, it's very similar to like the M685 from Aerotech, or I think it's like the M840 from CTI. Super similar motor. It burns about 10 seconds. I believe theirs are kind of in the same ballpark. But like when you design your own rocket motor, obviously additional things that you can do. You'll notice like on the second stage of like a Falcon 9 or any orbital rocket, you'll see that like the nozzle is much larger on the second stage rocket motor. And that basically improves the efficiency of the rocket motor. And so, when you buy a reload, that nozzle is spec'd for sea level, most likely. So I was able to actually fully expand the nozzle on the upper stage to give me that a little bit extra bump in performance at the higher altitudes. So the other thing to take into consideration is aero heating. With this rocket, I didn't run any fancy CFD. I pretty much, before, while I was getting into this, I scoured the internet to try to figure out what other people's rockets, what they were seeing and how were they returning after, say, a flight to Mach 3 or higher. And I gained, a little bit of, my own data points through like the workbench flights. And this kind of right here, workbench, which flew to 154,000 feet in 2018, and I think just under 150 in 2016. Saw about Mach 3.15 at 46,000 feet above sea level. So, it did not get incredibly hot, around 600 degrees. And there was very little aero damage on the rocket. Literally, the fins didn't even have any kind of paint on them. They were just naked carbon fiber. And I couldn't tell a difference before the flight and after the flight on the fins. And all I could see on the airframe was just a little bit of bubbling. So you can actually see, the shock waves setting up on this nylon shear pin screw. on the head of it, and you can see kind of how the shock is set up on the airframe off of that screw. All the paint is kind of bubbled up a little bit, but not even that bad. For mesos, I was definitely a little bit more concerned. The simulations were showing, speeds in excess of Mach 4. Granted, it was going to be at higher altitudes, but not only was the speed going up to the region of Mach 4 plus, I was going to wind up being above at those high Mach numbers for far longer than I was on my previous flights. And so, 1300 degrees, like 600 doesn't sound that bad when you start looking at like almost 1300 degrees for the temperature behind the shock wave when you're traveling that fast. So, going into this, I didn't really know what to expect. The one thing I did differently from my previous flights was I decided to paint the fins. And, the mesos leading edge, I was also surprised that honestly, the heating wasn't that bad. It was literally just the very, I say front, like 1/8 inch of the fin got cooked, like pretty completely cooked. I think it almost cooked the resin out of the carbon fiber fin underneath it. So, but back behind that, like there was hardly any damage, just a little bit of bubble paint, just like the years prior. So that's kind of the aero heating approach that I took. I think I got lucky, but I think basically setting up my flight profile to try to minimize that heating really helped. This is a flight profile from the video. You kind of got it. Like I was alluding to, that dwell times at the really high Mach numbers, particularly above Mach 3, I mean, it was almost 30 seconds. Luckily, the rocket is going up during that time, so you're getting into even thinner and more rarefied air while that's happening. But yeah, the numbers for the flight are kind of insane. To be supersonic for more than 2 minutes is kind of wild. So the design overview of the rocket. So down low is kind of it's a CAD cutaway of the rocket. You can see that it's mostly motor on both stages, but there's ample space for recovery, and if you're smart with the recovery design, we'll get into that on a later slide. You can still do traditional dual deployment recovery. These stages recovered at 20 feet per second. You didn't have to skimp on recovery speeds, even if you want to hit insane altitudes. You just have to approach it differently and kind of just eliminate a lot of excess. So, and then obviously do a lot of testing to ensure that everything works as you intend. But you can certainly recover rockets like this pretty traditionally. So the rocket's pretty small. For the altitude that it went to, I can carry it around without really a ton of issue. And I think I get the most bang for my buck in terms of pound for pound propellant for altitude with this rocket. So it was pretty cool. So anyways, you'll notice that the lengths don't really add up. This should be like 12.9, but that's because basically the back 5 inches or so of the upper stage slide into the inner stage. So you can see that down in here. All right. So I guess this presentation is to kind of show like my approach to these projects more so than to really delve into the design of mesos, because I could just probably talk about it ad nauseum for the whole day, and I'm pretty sure all of you would drop off of this. But I wanted to talk about order of operations, not in the sense of mathematics, but in how you should build one of these projects. I highly, highly recommend building the entire rocket first. And by building the entire rocket first, I mean literally build the entire rocket, everything, design the recovery system, the avionics, the payload, all of it. Design all of that. Actually build it, and then last, do the fins. And I think a lot of people probably won't like doing it this way because, you know, it's not a rocket project until it's got fins on it, right? I think a lot of people will say. But I think it's super beneficial. And the main reason why is, particularly for the sustainer, this is a chart of your center of pressure versus Mach number. Notice how much it moves. It moves almost 8 inches during the flight. And so you really want to make sure that you keep your center of pressure and your center of gravity relationship, you know, with your center of gravity out in front. Because if those flip at all during the flight, it's over, and it's going to be over very fast. So this bottom picture is the sustainer, and the motor is assembled, but the motor is assembled without propellant. So it's got the liner, the nozzle, the forward closure, the aft closure, right? All the parachutes, all the avionics, GoPros, the whole telemetry system. The only thing that I don't have pictured in here is I actually machined a little aluminum ring that is the mass of, the expected mass of what a fin can would weigh. I had some experience in making composite fin cans before, so I had a general idea of how much the fins would weigh. And so, I placed a little ring, mass simulator ring back here, and then balanced the rocket. And I did that also with the entire stack. Now this is with the first stage and the second stage with propellant in, because obviously your worst case CPCG relationship is going to be right at launch. And I'm doing a balance test here to try to get the right ratio for the full stack as well. And you'll notice that NASA does the same thing. Like this is the same sounding rocket, but you'll notice different fins on the Terrier booster. So like depending on their CPCG relationships kind of set up, they're going to swap fins as well. So they do something very, very similar in industry and in real life. So the other thing with the smaller rockets is I generally think that composites are absolutely 100% required. Simply, you're just not going to get the mass fraction without it. So if a component for this rocket can be made out of carbon fiber or fiberglass, I'm definitely going to go that route versus machining it out of aluminum. So because weight is obviously incredibly important. It's incredibly important for the booster because the less that the booster weighs, the more energy it's obviously able to impart into that upper stage. So you definitely want your booster light and then the sustainer light as well for obvious reasons. And so this is kind of like the process. I make like my own airframes. Like this is the airframe that wound up going into the first stage fin can. Here you can see kind of the layup patterns on the fins. So you can see that I do like this staggered pattern. I think on the second stage, 4 layers of carbon fiber went on. On the first stage, 6 layers. These all then get vacuum bagged. And so that's kind of the process. And yeah, the first stage fin can, this is a 4.5-inch diameter rocket, pretty big rocket, pretty big fins. I think the fins had, I want to say almost a 6-inch span. and the whole fin can only weighed about 3.2 pounds, which is like, you'll never get that with aluminum. So carbon fiber for the win on this. I spoke a little bit about recovery earlier as well. You know, I don't think like that you have to, you know, bring like one of these high altitude rockets in on a drogue in order for it to be you know, super efficient. Tripoli now requires descent rates of no higher than 35 feet per second. So you know, main parachutes are pretty much you know, they are 100% mandatory now. But like, it can be done, and you can still hit wild altitudes. And I hope that I've proven that to everybody. But you might just have to do the kind of like a more non-traditional approach to your recovery system than what you would do for like a sport rocket. But you'll notice that, like, you know, the booster has a 72-inch parachute, Stinger has a 48, and I believe the length of packing volume for the sustainer was, you know, I got a main and a drogue in plus probably 30 feet of a harness into 7 inches. And by unconventional, I use like basically this is like a single bay kind of fishbone approach, and I didn't come up with this. You know, this has been done by other teams. I believe even Aeropack did this as well. And it doesn't require the need for any kind of release mechanisms, like I believe like AARD. You know, you don't have to tether anything back. This is simply using charges and basically how you're packing the lines for your main and drogue to just ensure that they don't come out. I will say, like, this type of recovery system requires testing, and both on the ground and in the air to get it to work properly. But once it does, it offers really great benefits in terms of, like I said, packing volume, weight, all that stuff. So, and it works really well. So I did not have my main come out early on this flight or any other flight that made it above 100,000 feet, kind of using this system. I think this is nobody ever talks about this, but your launch pad is probably one of the most important, I don't know, depending on how long it is, like 15 to 20 feet of your flight. You know, besides the fins, this is what provides the guidance. This is what ensures that you have a straight boost. And on these types of flights, a degree or two off of vertical, and you're talking like many miles of travel downrange. So ensuring that you fly straight is super important. I designed this launch pad back in 2016 for some earlier flights. You know, when you go to Black Rock, it's very nice to be self-sufficient, have your own launch pad, or have a good friend who has a launch pad, so that, like, you know, you can have priority over it, and you know, it's yours. You know how it's set up. You know the rail's straight. You know that it's dialed in. It's very important. And so, you know, kind of throughout the years, as I've flown rockets off of it, particularly the high altitude ones, I've made improvements. So I definitely hold my launch pad near and dear. It is its own little, I don't know, engineering marvel project that I've kind of worked on here and there over the years. And so, yeah, building the launch pad is super important. If you build one of these projects, I think you're going to be building your own pad as well. So, all right, and then kind of just to show that, like, look, the rocket is literally like, I know this is kind of cliche, but like it is the tip of the iceberg. The equipment needed to build a rocket like this, and then like the skills that you just have to attain by doing, it just takes a lot of time and a lot of effort. And a lot of people always ask me, they're like, everyone always asks me like, oh man, like how much did this project cost? And honestly, to tell you the truth, money was not money was not the biggest cost. Sure, it cost some money. I will say that like it, there are far more expensive like skiing's an expensive hobby, mountain biking is an expensive hobby, um it wasn't, outside the spending of like those two other sports. But the time involved was insane. um the time involved was legit a second job, like easily. On the bad weeks, it was another 40 hours on top of 40 hours of regular work, for me. So it was just really long days, long weekends, long nights. So I think the biggest investment for anyone in this is not going to be the space. I don't think it's going to be the money. It's really going to be your time. So, and with that, I think I'm done. I have no idea how much time. Oh my gosh, I did okay. 10 minutes left? I don't know. uh, so let's see. You guys there?
Yep, we're here. Can you hear me, Kip?
All right. Yeah, cool.
You want to
Yeah,
take
now
some
I can.
Q&A?
Yeah, let's do it.
All right, let's do them in order. So first question is how much EX experience did you have when you started building the motors?
None.
That was a long road. And you just kind of went through some of this, but if you had to estimate how many man hours, like any idea?
For the motors?
The whole project.
For what? The
The whole
what?
project, yeah.
The whole project? I don't, in the thousands. It had to be. I mean, I don't know. I'd have to really think it up, think about it. But yeah.
It's a lot.
Yeah.
Bob mentioned that it looked like it tumbled for a long time there at the end as it went up, and he wanted
Yeah.
validation. The assumption is there's not enough air to make the fins have it stable. Is that correct?
Yeah, so you'll notice it started to spin up. It's a moon burning propellant geometry. So the core of the basically the core running up through the motor is off to one side. And so you're kind of like, during the entire motor burn of that second stage, you have this like off balanced mass as the rocket's spinning. And the whole, goal is to hope that you got the fins on straight enough that the rest of the components are laid out, along the roll axis of the rocket evenly, that you try to minimize the spin, because the spin will eventually turn into, a wobble, and the wobble will turn into coning. And if that happens at a low enough altitude, it's going to be a huge hit on performance. So yeah, that's another one that's kind of left up to chance. You try to get the fins on as straight as you can, and cross your fingers. Yeah.
There was a question about upper stage ignition. Was it head end or through the nozzle?
It was a head end. Yeah. Yep. It was a head end ignition. That simplified a lot of things. Other than the fact that you have to put the motor together at the launch pad, which, for safety reasons. So, I mean, that's the only thing that really complicates it.
My favorite question: as a 13-year-old who loves rocketry and lives in a state with 0 active NAR clubs, and the highest waiver nearby is 18,000 feet, but wants to fly stuff like this, but is restricted to L1 motors, what would you recommend I do, Kip? Or is it just not feasible?
I mean, I think like, look, there's a lot of things that you can do on the lower end of the motor, like scale. Like you can still fly two stagers, you know, and and you can do some really cool projects with the smaller motors. And oftentimes they're more fun than flying these big projects. I think I had more fun flying test tube than I actually did flying like mesos. I mean, it was just, yeah, it's a lot of stress. So, yeah, I think there's a lot of cool things you can do with the smaller motors. I think that people typically don't do, and you don't see at launches, like air starts, clustering, staging. How often do you see a two-stager composite propellant rocket fly at a launch? Maybe one a day, couple a day. At a large launch, it could be more than that. But I would do that kind of stuff. Like even if it's not going to go super high, they're still super fun, and you learn a lot.
Good answer. Michael wants to know if your motor build, payload technology, and/or ground control software is available in open source.
I haven't open source anything. I think, I haven't open source anything. No, not really. I mean, I'm willing to answer questions though. So, you can hit me up on Twitter, Instagram, and get my contact info. Yeah.
Awesome. John wants to know if you had any mentorship while working and building on your own motors. Like, how'd you figure all that out, and how did you get there?
Yeah, so I did. I had one mentor. Actually, to this day, I still have not met the man in person, but through other folks in rocketry, I got introduced to Al Gonsalves, and he helped me with quite a bit of stuff, particularly while I was getting started. And even though it was like over the phone, he was incredibly helpful, even when like bouncing ideas off of one another. He was really helpful in helping me develop the igniters for this rocket. I had a lot of issues with motor ignition, so he helped me quite a bit on that. The other thing that was super important for me was getting access to the experimental forum and for rocketry forum and just dissecting that. You can learn so much from reading those forum threads, and even if it's like 8 pages of garbage posts, you will find those 1, 2, 3, 4 posts where somebody just delivers like this awesome nugget of information that you can go and apply to your own motor making. And then also, I just read a lot of books. I bought every book you could buy for making rocket motors from the hobby, and then even a few college texts. So
Awesome.
Yeah.
2 related questions, Kip. First one, what is the secret to getting a recovery charge to work reliably in a vacuum? Followed up with, what was wrong with the ones that you found that failed, that you explained?
Yeah. So the problem with the ones that I had was I basically, the relationship of where the E match is in the pile of black powder was incredibly important. When the E match was too far down, it would light the black powder down low and basically not burn, but just it basically eject the remaining black powder out of this like long brass tube that was used for the ejection charge. So it wound up becoming really important to place the E match at the top of the powder so that it actually would burn from the top down. And then the charges worked reliably. So yeah.
And what about getting them to light in a vacuum? Anything fancy there?
So getting them to light in a vacuum, like basically there have been write-ups done by Jim Jarvis, and basically using pretty much like a long tube to create essentially what is back pressure that allows time for complete combustion of the black powder before it is ejected out of the tube. So I think the going term for these is cannon charges, is what people call them, or tube charges. So if you can type those into Google and go to town, or in the rocketry forum, and I'm sure you can find some additional information on that.
There's a question here. What was the core of the fins that you were showing that were carbon?
Carbon.
Carbon with carbon layup, huh?
Carbon with carbon layup. Yeah. I think I bought the plate from Dragon Plate, so you can go online and you can just purchase plate. It's really high quality. It's super nice stuff. I think the 250-degree plate.
There was a question around the accuracy of the measurement of 293,448 feet, and they were
Yes.
asking about the GPS or technology used to measure that.
So that was a K3 GPS that Vern Knowles sells. He is the head of multitronics.com. And he will not tell me what the GPS chip is. He's keeping that a secret. So I don't know.
What's next for you, Kip? What's the next goal?
To fly higher. No, I mean, I would love to fly higher. I think I want to do it with this pretty much the same package. And that basically entails, like I talked about in one of the slides, is, long burn motor in the second stage is super important. In terms of delivering that power efficiently. And so I think I can go quite a bit higher if I double the burn time on the second stage motor. But that's going to radically change the second stage motor. So there'll be a big project. I don't even know if I can do it, but I'm going to try. So I think that's next. But while I'm working on that, I'm going to fly this rocket again this year. Probably at a UROC launch, so out of Black Rock. Yeah.
Awesome. Well, Kip, we are a few minutes over.
Okay.
I want to thank everybody for joining. And if you have additional questions for Kip, as you heard him earlier, find him on Facebook, Instagram, or some otherwise. And
yeah, I think there's links to like my Twitter and Instagram, and those are, I check those. I don't have a lot of friends, so you can hit me up there, and I'll be happy to answer your questions. So
awesome. Well, Kip, thank you for doing this evening. Wonderful presentation, and thanks for everybody that joined.
See ya.